Um, yes, Diganta, did you want to say something?
No, I just said hi all.
You better wait for the hi all. There's only one person today. Yes, Diganta, did you want to say something?
There's some double audio, right?
No, no,
Hi
no,
all.
no, no, no. I know. You better wait for the hi all. There's only one person today. Yes, Diganta, did you want to say something?
There's some double audio.
No, no,
Hi
no,
all.
no, no. I know. Okay, now there won't be.
Yeah, it was the recording which was feeding back, right?
That is right. So I'm recording a live stream on
Okay.
YouTube. Okay, so if I do that, otherwise this conversion of when I record it directly will take forever.
Right,
And
that
the
makes sense.
file is very huge also. An hour of recording is about 137 megabytes.
Uh, I also recorded the last class and I finally got it uploaded.
You did, okay.
Yeah. Where do I
Oh, okay, that's good.
So it crashed like 7 times.
Yeah.
See my Wi-Fi. I did it on my
I think
phone
there
network.
is Zoom has this nice feature. I know maybe it is there on the other things. I don't know. But
No,
you
I don't. So Teams also has it, but thing is, it won't let me share this recording very easily, or upload it to YouTube. Zoom has a very nice feature where they can just directly stream it. I don't think
yes.
anybody else has that.
Mm.
Google Meet has it in its premium version.
Okay. Yeah, the premium feature. Yeah, I
Yeah.
see. Um,
Let's see. So there are.
so I have also uploaded a version of the previous thing to YouTube. Um, but I think in my version, some of these questions didn't come through. So between both of us, we will have something. So Parnika is asking, do we not have offline class in the chat?
Well, okay. Yeah, I'm going to wait. Today there is no offline class. Okay. And I will tell you, I know that, well, let's wait because if there are more people, then I don't have to repeat myself. I'm going to wait till today, 3:35. So, I mean, maybe 3:40, another 5 minutes because there were more people. There are all kinds.
Yeah. I guess we can start it around 3:40 or something.
Yeah, 3:40. That's what I'm thinking. I see one new person here, Vardhan. Vardhan, if you can unmute, is this your first class? You can't unmute. Oh, this is my second class. Okay. Oh, there were Eritrea is here.
Oh, I think, yeah, Vardhan was there. I think
No, he said he was there for one. I mean, we have had only two, right? Correct. Yeah, we'll wait till 3:40 and then we'll start because we are recording it anyway. Huh? So I think things will take. I think after 24th we know how many people are
yeah.
taking it. There were two, three other people. Bijayan who attended all the. think he's not here. Maybe you can send a reminder. Bijian is here. Maybe then I can share, and then I want to say a few things about that question that Anika raised. I will address. So you can see my screen, right? So you see, there are two reasons why we are going to be having, at least for the next couple of weeks, the classes will all be online, okay? Because I'll be traveling starting tonight till February, till February 16th, okay? 14th, yes. So today is 21st. So 1, 2, 3. Yeah, a few classes, yes. So the next physical class will be on the 18th. Okay. So, yeah, so Diganta, anyway, Diganta's classes, lectures will have to be online. But what I'm planning to do is, even when, since both of us will be on, away, therefore, starting February, till February 18th, okay, that is till actually February 13th, the classes will be online, okay? Now, once I get back, it will be physical classes, even when Diganta will be lecturing, okay? So I plan to have, he will be talking remotely, but we'll all gather physically here. That's how I have done it earlier. And so after February, starting February 18th, all classes will be physical classes there, and I'll be there. Okay, so that's the idea. So from today till February 13th, it will be remote class only. Now, I will be in California time zone. Okay, therefore, just for starting 23rd for these till 13th, the 23rd through 13th, for those classes, we want to have an alternate slot. Okay. I mean, a slot, you can still do it on Tuesdays and Thursdays. You can keep it on Tuesdays and Thursdays. But I want it, some time that is convenient for me. I'm willing to do early. Okay. Either it has to be night here, in which case it will be early morning there, or a morning here and night there. So the next class will be on the 23rd. 23rd, Diganta will continue to lecture. Okay. So maybe for the 20, well, let's see. So I want a time. Okay. My first proposal is maybe 7:30 p.m. here, which will be like 6 a.m. my time. Or even if you don't mind later, like 8 or 8:30 p.m., that is 7 a.m. my time. That would be preferable for me. But that is something that that I'm proposing, that is 8:30 p.m. as the first option, or whether it should be a bit earlier, means 6 a.m. is also okay with me. I think earlier will be a little bit problematic. But if you don't mind, if you guys don't mind having morning classes, I'm okay with night there for me. But I'm not sure how many, because there'll be conflicts in the morning with the rest of the classes and so on. So that is my proposal, and I appreciate your cooperation on in this regard. Yes, till that time, we don't have to decide. I made a proposal. Shauriyam, you could communicate with the people. Once we have on the 24th, we will know. Okay. So for 23rd, we just have to decide tentatively what time it will be. I ask again, is 8:30 p.m. okay for people that are on the call right now?
8:30 p.m. is fine with me. What about everybody else?
Yeah. Or yeah. Or what you can, no, it has to be like that, because if I want to use Zoom, then I'll have to start it. Okay. Maybe for uh, 23rd, even see if it's the same time as we have selected here, that is 3:30 p.m., that will be like 1 a.m. So that's 1 a.m. there. Mm. It will be 2 a.m. 2 a.m. there. So that is a little bit too late. Okay. 3:30 p.m. just will not work. Okay. I'm okay with even 5 a.m. there, 6:30 p.m. So first I'm asking, people have to respond. Okay. Let me ask the negation of the question. Having it at 8:30 p.m., is that problematic for anyone? If I hear no answer, I'll assume that it is okay. Well, I guess it's okay. Um, Vardhan asks if we can have morning classes at IST. Okay. Morning classes is okay by me. Huh? How early is something that we have to decide. So rather than spending a lot of time, Shauriyam, yeah, we can't, you will have to coordinate. Can I?
Yeah, I'll create a timesheet and ask everyone to block what they count.
Okay.
So there is a WhatsApp group, right? We can just create some poll
That
over
is
there,
right.
maybe.
That's right. Yeah.
Do that.
And so at least for the till for the 23rd class, I'd like to it be decided as quickly as possible. Let's see how many people are here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so yeah, so you will have to communicate and then let me know. Okay, so I'll stop sharing. I've stopped sharing. Okay, so we will determine and we'll make an announcement. We can use the same Zoom link. Okay, I've created a recurrent Zoom link. Okay, and I'll do that. I'll make sure that I will record all the lectures, so people, even if they miss some of the classes, then you can certainly listen to them, listen to the recording. But let's hope that we can all agree on, we'll be able to agree on suitable time for the next 3 weeks, and then so that we can all participate remotely. Okay. Uh, Fine, then you can start sharing, Vedanta, and you can start.
Yeah. So there is some disabled attendee screen sharing message.
Or maybe I have to do co-host.
Yeah, maybe. Or you can enable attendee screen sharing, or either way I think should work.
What more is this? Let me make it. Yeah, now you should be able to. Sorry.
Okay.
Good. I think most of the people that I was expecting are here. So
All right. So I guess we can start. So can you see my screen right now? It should show the
the
Zoom
whole
page
page.
itself.
Yes.
Yeah. Yeah. Okay. So let me just connect my Wacom tablet. And I will start.
Also, just in case, the first time this term I'm using live stream. So as a backup, I'll also record.
Uh,
Yeah. Go ahead.
okay. Sure. So not this one. Sorry. Good. So we were basically looking at this a very broad introduction to machine learning, and we covered some number of things. I'll just take maybe a minute to quickly go over what is it that we covered last time. And what we covered is that we introduced machine learning as a problem. Why do we? Why? What is the kind of situations in which we need machine learning, right? So these are situations or problems where we have a lot of data, but we don't really have any other way of defining or making a headway into the problem. So imagine, learning to classify images of a cat. You don't really know what a cat is, but you have a lot of data, a lot of images about what a cat is, right? So we thought, okay, how do we tackle this problem? We have a lot of data, and there is some function which can, abstractly speaking, there should exist some function which can, generate this data. But how do we actually find that function? And the way we do that is using things like parameterized function approximators, or at least one way to do that. There's a lot of other ways within machine learning. And these parameterized function approximators, they typically look like this. They are functions with some parameters stuck within them. And if you change the values of these parameters, the behavior of the function would change. We introduce deep neural network as a parameterized function approximator itself, right? So it's this kind of a network which takes various values over here, multiplies them with weights, and moves along each layer, and so on and so forth. And we have discussed, that these deep neural networks, we expect that they'll work because they have this layer wise structure, and each layer we kind of expect to capture some level of detail, patterns at various levels of detail in each layer. And then what machine learning turns out to be is an optimization problem, right? So we have these values of parameters. Finding a good function or a good deep neural network is just to find these values of parameters, these values of weights and biases. And we'll phrase this problem of finding the weights and biases as an optimization problem by defining a loss function which should be lowest for the particular values of weights and biases, the particular values of the parameters for which our function f behaves as dictated or as the data would expect such a function to behave. Right? So the function f should behave in alignment with the data. And this L, basically, you will take the parameters, construct function f, measure it on the data, and say whether it aligns with the data training data or not, and then return a score which represents how well it is aligned. So this is the high level, and the next few slides that I have, I'll repeat the last slide from the last class, but the next few slides that I have kind of shows various paradigms of machine learning, and via some high level examples, how what L turns out to be, or what L kind of looks like in each of these paradigms. Okay. So let's take the first paradigm, supervised learning, right? So, okay, before that, I think I should ask, is there any question? Is there any, doubt about the whatever we had talked about last time? Is there any detail that you want me to recap a bit more before jumping into the rest of these slides? No? Okay, sure.
Okay, go ahead.
Yeah. So, the most sort of first or easy to understand paradigm, I guess, is this kind of a supervised learning paradigm, right? So here your data are kind of input-output pairs, So let's take an example, right? So suppose we have some data set which is the age and weight of various individuals, and some measure which is the kind of risk of heart disease for all these individuals, right? So each point in your data set is a tuple of all of these values AI, WI, and RI. And what you want to do is you want to now develop some system that will take in an individual that is not seen before, take the age and the weight of that individual, and kind of give out a prediction of the risk of heart disease for that individual, right? So so how do you do that? Well, you come up with a parameters function approximator f, right? F would take in AI, WI, and given some theta, it would then give you some value of RI, right? Now the question is, okay, I mean, is this parameter function approximator any good, right? How do we know that? We can do one way of knowing that. In fact, in some sense, the only real way we have of knowing that is to see what it does is on our data set, right? So what happens in our data set, if we take each of these tuples, AI, WI, and RI, we send AI, WI to F, and we ask, okay, is the output of F actually close to this particular RI from our data set, right? If it is close, then at least we know that the F, the way that it behaves, is aligned with our data set, and that's good for us. If it's not, then that's bad for us, right? So we can formalize this. We can actually write an expression that sort of captures this, which would just be this, right? So the absolute difference between the output of F for a particular AI and WI and the corresponding actual RI from the data set, right? And if this value is low, that means that our function F is sort of well behaved with respect to the data set. If it's not, then it's not well behaved, right? Now, if you take this average of this value over the whole data set, what you end up with is an expression which, when it is low, it's going to represent that, okay, we have found a function that is good, otherwise it's not going to be good, right? Okay, and notice now that this expression, the only real variable is this theta, correct? Because AI, WI, RI are all constants, they're all fixed. I mean, the data set is fixed. So AI, WI, RI are all constants. Theta is really the only variable. So this whole expression is just a function of theta. And in fact, it's a function of theta where we want a theta for which the value of this function would be the lowest, right? So now what we have is really this complicated function of theta, and we want to just find a theta which will reduce the value of this function, right? So this is the kind of the paradigm that we're working with, and this is why how we phrase machine learning as an optimization problem. In most cases, we have some data set and we construct a loss function out of it, out of which we'll find this value of theta, right? So far, this actually makes a couple of things in this picture that we were this running picture that we have had previously a bit clearer, right? So if you remember, the running picture that we had clearly previously was saying that you have some data set D, and we have some kind of an algorithm, which then should give me some kind of a function F, which will, which has been trained on this data set and is learned to do whatever was captured within the data set, right? So this data set could be images of cats, could be this age, weight, and risk tuples, and this F should now be a good predictor for cats or a good predictor for risk of heart disease. And now last time we had spent some time on saying that really this F is going to be a parameterized function approximator. So this F is really just something like that looks something like this, right? And then the question now really becomes not for finding F, but rather this black box, this whatever this algorithm should instead just give me a value of theta that works well. Now we have some insight as to what this algorithm is supposed to do. This algorithm is supposed to do nothing other than take this data set and construct an L, optimize this L, and this optimizing this L would give me a value of theta that should work well, right? So this algorithm is just going to be some kind of an optimization algorithm which is going to find the optimal value of theta for this given L, and this L is going to be constructed with using the data set. So this basically is now giving us window into what this algorithm is actually going to do. And now again, remember that last time we had said this F is going to be a parameters function approximator. The particular parameters function approximator we would be interested in is a neural network. But all of this will still work for any other parameters function approximator. So take whatever example you want at the back of your mind. A linear classifier, a quadratic function, anything would do, right? Okay, so this was how we set up a machine learning as an optimization problem. Just to make things a bit more maybe concrete, I'll give a few more examples of this in a few of other kinds of settings, right? So of course we have been talking about classifying cats and risk of heart disease prediction and so on and so forth, but that machine learning can do a lot more right now. In some sense, there's all the chat GPT chatbots and all of these kinds of things. It seems to do a lot more than that. So a question that one can ask, and I think sir had also raised this point last time, is that this kind of a optimization problem finding theta framework, does it really work for all of those kinds of settings as well? It doesn't work for all of machine learning in general, because sometimes it's not as simple as setting up an optimization problem, but it's actually widely general. In fact, a lot of different generative AI kind of training can be thought of as this. A lot of different reinforcement learning paradigms can also be thought of this. And I take a couple of slides to kind of bring that point home by giving a few more examples of some slightly more complex problems and how those can also be reduced to an optimization problem on theta, right? So let's take an example of some unsupervised learning, right? So previously, if you remember, data was consisting of input and output pairs, right? So we had, your AIWI, that's your input, and RI, which is your expected output, right? But in many situations, we don't really have an output within the data, right? It's very hard to kind of have this kind of a neat data set with both input and expected output, right? So we may have situations where data have only inputs. So for example, I might want a system that can generate a random human face that has never been seen before, right? Now, if you know this kind of whole, the first, very surprising example of generative AI that a lot of people were caught off guard was this kind of DALI and all these image generation models, right? And they can do something like this, right? They actually do something much more sophisticated than just this, but they can definitely generate a random human face. So suppose we want a model, some system like that, right? So something that will generate a random human face. And what do we have as a data set? We just have a huge class of human faces, right? So there's this input, huge data set. There's really no input output pair here, right? It's not like we want our system is supposed to input a human face and then output something. No, right? Nor does our data set have any kind of input output points or anything like that, right? We just have a huge heap of human faces, and we somehow want to train a system that will generate quote unquote a random human face, right? Okay, so what is the key difference between generating a random human face and a random image? Now, if you think about an image, as we had talked about last time when we were talking about feeding images into neural network, for us, an image is just going to be a point in Rn, right? So where basically each real value or each value of the pixel here, just talk about black and white images for simplicity, but each value of the pixel is going to be one component in a huge vector, and this huge vector lives inside some Rn, right? So this n is just going to be the number of pixels in your image and so on. So selecting a random vector from this Rn is definitely not going to solve our problem. That much is clear. But selecting a random human face, what does that look like from this perspective? Really, what we want to do is we want to find a subspace of this Rn and then sample that subspace to generate a random human face, right? So definitely human faces lies within Rn, this kind of an Rn, images of human faces, but it's not all of the Rn, it's some subspace of the Rn. And we want to sample that subspace and find a human face, right? And that is going to be a fairly complicated subspace. So if you imagine this is your some 3D kind of view into your Rn, the actual subspace of humans' faces might look like some really complicated surface or shape over here, right? And we want to sample this a bit. So how do we do that? Well, one way is to somehow learn a function that will take a simpler space, let's say Rk, where k is less than n, significantly less than n, and it will take this simpler space and embed it into Rn to generate this subspace. So it will basically take Rk, which let's say is just a square surface, and map this into Rn so that every point in this square surface lies somewhere within this subspace, right? So if we can find a function that does this, then what we can do is simply sample over here and take this function f, and we should get back to this more complicated subspace, right? And this function, when we sample something over here, should give us something over here that lies in a subspace. So it should really just give us a human face. So how do we find such a function, right? Okay, that's a good question. But let's ask maybe a slightly simpler question, which is, what properties should such a function have? It should actually have, it should come with another function g, maybe, right? I mean, so for example, one thing that this function cannot do is just take this whole space and collapse it down into a point, right? So that is not allowed. So, okay, just a second, maybe yeah. So one thing that this f cannot do is it cannot take this thing and collapse it down to a single point, right? So that is definitely something that we should not allow, right? So this should not be allowed. Okay, what does that really mean? That means that whatever f does, they should, in some sense, I mean, one can come up with this kind of a thing a bit more carefully, but uh, one way to prevent something like this from happening is to also insist that along with our f, there's going to be a g that is going to really take this more complicated subspace that we wanted and put it back into the square, right? So now we know that this embedding is kind of 1 1, right? So if we have both of these kinds of pairs, if we have found a function that satisfies this kind of property, we have an f, and we know that there is a function g, so that if you take f, you get human faces, and when you put a human face, g gets you back some point in f. Then we are done, right? So geometrically, this of course makes sense when we think in terms of Rn, or I don't know. I mean, to a certain extent, it makes sense. But also there is another semantic way of looking at this. Like if you think about it, a human's face is really defined by some set of parameters, right? Of course, no, it's not like all human faces are identical. If we knew that all human faces are perfectly identical, generating an image of a human face is going to be trivial. Just generate that particular human face, right? But there's some variability, but that variability is really controlled by some set of parameters, right? So maybe it's like the distance between the eyes, right? Maybe it's the color of the eye, the eyelids. Maybe it's the width of the nose, right? So the size of one's ears, and so on and so forth. So we know that there is a lot of variability in human faces, but this variability is captured by a limited number of parameters. And the number of such parameters is going to potentially be large, but it's not going to be as many parameters as their possible combinations of pixel values. It's going to be definitely smaller than that, right? So that perspective also lends credence to this kind of a model where, in some sense, this f it's remember this f is taking some rk to rn. This rk is going to the space of these parameters, right? So each point in rk is going to be some set of values for distance between eyes, color of eyelid, size of nose, size of mouth, size of ears, shape of the face, and so on and so forth, right? So this is the kind of intuition that we have. And then f and g, what they're supposed to do, f is supposed to take these parameters and generate a face, and g is supposed to take a face and extract out these parameters, right? Okay, so now we have this whole setup. How do we actually find this f and also this g, right? So we want both the f and g. So what we do to get that is you know we just encode this kind of a situation into a loss function, right? So we say that, okay, we'll set up f and g to be parameterized function approximators, right? So neural networks. But it can, if you're it can be any kind of parameterized function approximator, really, right? And the idea is that, okay, so technically f and g will have a different set of thetas, but it's fine. You can also have f and, like, this theta can just be a common vector covering both an f and g. But the idea is that if you now take any xi, and remember xi is just an image of a face, apply f. So okay, I think I have written it the other way around, but yeah. So let's say that the function taking face to our parameters is f, and the function taking parameters to face is g. Okay. So we apply f, and of course this parameter is by theta. Then we'll get some set of parameters, right? So we get this size of nose, whatever, whatever, whatever. And then we apply g again to this and go back to, an image, right? Then what we should come to is something that was close to our original image xi, right? Which means again that this particular expression that should have a low value, and which is exactly what I have captured in this loss function. So the average value of this expression should be low. So this loss, all that it says, all that it encodes, is that if you optimize this loss and come up with a low value, you're going to come close to the situation given in this diagram. And once you are coming close to the situation in this particular diagram, you would essentially have a pair of functions f and g that behaves in this kind of a way. Now, this is not a foolproof or a complete description of the class of techniques that actually do things like this. They do a lot more to prevent some various kinds of corner cases and various kinds of collapses and so forth, right? Um, there is a lot more that goes into getting a technique like this to work well, but this is the central idea. And you can imagine we were starting out with a much more complicated problem, but what we really did was this kind of a train of thought where we said, okay, here's the function that we want. Here is the properties that we care about for this particular function. Let's try to write all those properties that we care about in terms of as a loss function or as a value, as an expression in terms of various points of the data set. And then that gives us a loss function, which we can then optimize. And then that optimization process is going to give us these functions back, right? So it's really this kind of a thinking that'll let you take a lot of complicated real world situations and boil it down to uh, a loss function, and then optimize for that loss function and find parameters or functions for that have various kinds of properties, right? If this feels like a very general approach, which is because it is, I've been kind of very high level and sort of hand wavy throughout this description of this particular unsupervised learning problem, and there's a lot of details that goes into getting this to work, but you can imagine that this kind of a framework should be applicable in a lot of other problems, right? You can have more complicated diagrams and more complicated loss functions expressing relationships within those diagrams and solve for various functions using this kind of an approach. Okay. Any questions so far?
Yeah, in this framework, I have a question. So F and G have to be prescribed a priori, correct? Okay.
So F and G are both neural networks in this case. So F and G are both parameterized approximators.
Okay. So yeah. Okay. Yeah.
Yeah.
So you could
So basically, we have one neural network that takes like this, and then another neural network, that takes goes back like that, right? And all we are asking that is that both of these neural networks should, compose well, and at least on this particular data set that we have, it should compose to give us identity, right?
So you learn it via the theta as
correct. Yeah, and the thetas are again the weights and biases of these guys. So
any other questions, guys? Okay.
Yeah. Okay. Okay. So third and final example of just to of this kind of a framework of looking at ML as an optimization problem is this example of reinforcement learning. I'll not have as much details about this, but this is again a very wide and very powerful um, uh, branch of machine learning. And what this says is that take any problem which you can define as a one player game. So it's a game between a player and some environment, let's say, right? And the environment makes then the environment basically just makes probabilistic choices based on the current state. So the environment is Markovian in some sense, right? So if your problem can be defined in this kind of a way, and if you can assign rewards to various moves, you can say that now I want a function f that represents a strategy for playing this game. So that represents the particular single player's strategy, which gets as high a reward as possible, right? So the loss is really just, what is the expected reward one can obtain when playing using this particular strategy F. And then this F can itself be a parameterized function approximated. And you can now optimize for this theta and get an F that is a strategy that is good as playing this particular one player game, right? For instance, you know, what can this solve? So for instance, you can define playing any kind of a board game, let's just say Go, because Go was really the first example in which this worked really well by Google DeepMind and AlphaGo basically. But let's just take Go. You can define playing Go as this kind of a situation, right? So you set your opponent to do, so let's say follow a particular fixed kind of strategy, right? Or the opponent can do something random. The opponent can be the till then best known engine to play Go. The opponent can be an earlier version of your parameters function approximately that you've trained well. But if you fix that, then now it's a one player game, right? And then your opponent, all that the opponent is doing is taking a look at this kind of the current situation of your board and making some decision that is Markovian, right? It's going to make some decision based on the current board situation and apply some, and that decision can involve some kind of a probability, right? So it can take certain moves with certain probabilities based on the current board situation. And now for any given strategy that you have come up with, you can simulate a large number of games and come up with an expected chance of you winning. So you set up your reward so that if you win, you get a high reward. If you lose, you don't get a high reward. Let's just say you can come up with an expected chance of winning, an expected reward that you gain by doing a large amount of simulation. And then that is your loss. Like you want to just maximize the chance of your winning, and you can optimize your parameterized function approximator in a way so that your strategy learns to play those particular kinds of moves that will actually give you a high chance of winning, right? Again, there's a lot of details here that I'm just very at a very high level skimming over, but the point that I want to say is that this can be thought of as still as an optimization problem on your parameter space theta, and it's very very powerful. So I've talked about Go, but in fact a lot more practical and interesting problems can be thought of as one player games, right? So for example, finding a matrix multiplication algorithm can be thought of as a one player game where the moves are basically uh, guessings that your algorithm will have a particular kind of step, and the reward is just going to be, okay, if you follow these steps, do what you end up, is that really a matrix multiplication algorithm or is it doing something different and random, right? Finding various artifacts in various program analysis situations is also can be thought of as this one player game. Turns out that doing analyzing protein folding can also be seen as a one player game, and that is what led to the recent AlphaFold and the Nobel Prizes from that Google got, right? So this is a very powerful technique, very non-trivial to actually get working in various situations. Like it's a lot of work. Like if you look at the time that that was between solving Go and solving protein folding via the same technique, you would realize that there's a lot of technical details that need to be figured out and worked out for this to really work. But at a high level, at a theoretical point of view, from a high level kind of framework, this is basically still an optimization problem, right? Okay. So, any questions so far?
So,
Yeah.
are you assuming that like expected reward is negative? Because typically we will minimize the loss function, right? But
Yeah, 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 yeah.
we
So,
might
so
not
I
want
didn't.
to.
Yeah, correct, correct. So there should be a negative sign here. So yeah, that's a good catch. I mean, I kind of didn't notice that while writing, but while saying, I thought that I'll not go into that just to keep the flow of things. But yes, there's so when you assign rewards and then the loss is kind of here is kind of going to be the negative of the expected reward that you're going to get, right? So this is the expectation when you play according to your strategy theta. strategy given by FC. Yeah, does that answer your question?
Yeah, yeah.
Yeah, so there's a negative sign here. Yeah. Any other questions? Okay, sure. All right, so now I want to give a bit more details about setting up a simple digit classification example using uh, using this MNIST as a uh, the MNIST data set, basically, right? So, okay. So I think you've seen this MNIST data set as in this previous slide where we talked about these various layers of the DNA and intuitively what each of these layers kind of do. And so I'm not repeating what this MNIST data set is, but essentially what we have is a bunch of handwritten digits, and we want to classify which, for a particular image of a handwritten digit, which digit is it really, right? So what do we have in terms of data sets? We have a bunch of input images. So I'm going to call, or I'm going to index these input images by J, and we have a class Cj for each of these input images, right? So, okay. So now, if you remember previously what we had talked about when we talked about how a DNN is supposed to do something like this, we had said that, look, what this DNN is going to do is it's going to take this input image. So maybe I'll just repeat it over here. So it's going to take this input image, which is really just this grid of pixel values. And each neuron in the input layer is going to take the value of one particular pixel, right? And then there are many hidden layers. And finally, there is going to be some neurons which produce some scores. And there's going to be one neuron for this code, producing a score corresponding to each class, right? So the output of the DNA is really going to be 10 such neurons, and I'm going to call them Y0 to Y9, right? So each of these neurons is going to produce a score that tells us what the value, or to what extent the neural network thinks um, the chance, or loosely speaking, what the score the neural network will give to the possibility of this particular input image being in that particular class, right? So intuitively, uh, this kind of a, let's say, y6 j cap is going to be the score the neural network would give to the possibility that j is in class 6, right? So, or that is, the image j is really an image of a 6. Okay, now remember, what we want to do is we want to finally train this neural network to classify images correctly, right? Now, if you go back previously to our example of supervised learning that we had talked about some slides back, remember this loss function was really just looking at the difference in output values of our function f and the actual output that we have, right? But here is an issue. This difference, um, it's actually very nicely well formed if the expected output of your function is just something that is continuous, right? If the expected output of my function is a class, which means class is just a discrete value, it can be 0, 1, 2, or 9, right? 0, 1, 2, 3, 4 up to 9. Then saying this doesn't really make too much sense. We can still phrase this as an optimization problem, but the issue is that that would now no longer be a continuous optimization problem. And a couple of slides down the line, we'll see how we crucially exploit some nice properties of this L, which is that it should be, continuous and differentiable almost everywhere, to solve this optimization problem, right? So because so far we've only been phrasing it as an optimization problem, we've not really talked about how one would go about solving this particular optimization problem, right? So given that we want some properties out of L, and these are the two properties that I'll mention, and I'll justify why we want both of these properties in some later slide. Given that we want L to be continuous and we want L to be differentiable almost everywhere, this leaves us with a problem. Because, okay, we know that each of these images can be only one particular class. We can somehow interpret the output of the neural network to select one particular class, but then the difference in the values of these classes is going to be a discrete value, and that is not something that we want. We want a continuous and differentiable kind of loss function, right? Okay, so then how do we do this, right? What we'll do, okay, so one thing that we could have done, for example, is to just select from this y0 to y9, we select the one that was the largest, and we declare that the neural network simply says that whatever is the largest, whatever it has assigned the largest score, that is the one that the neural network thinks is the correct class. But then that leads to this particular issue, right? So how do you compare, when you compare it against the actual correct class, you'll only get integer values, and then you get an integer valued loss function, which or a discrete valued loss function, which is not going to be continuous, and it's going to lead to issues for us, right? So instead, what we want to do is we want to convert the output of this neural network, the scores, into probability functions, right? And that is going to allow us to extract more information out of the neural network, and it's going to help the optimization problem later on. And I'll explain in a bit exactly how that's going to work, right? Okay, so to motivate this a little bit better, let's imagine two situations. So let's imagine a situation where we have, let's just say the classes 0, 1, and 2. Let's say the neural networks assigns score, two sets of scores to these things, right? In situation number 1, we have a score 10, 5, and 6. And in situation number 2, we have a score 100, 5, and 6. So my question to you is both of these two situations correct? Or is both of these situations equivalent? Should both of these two situations be equivalent? What do you think? I mean,
Yeah, like
is the neural network telling us the same thing in both of these two situations, right?
no, like in the latter case, we can distinguish zero like more. Like we can see with more probability the answer is zero compared to the first
Exactly.
one.
Exactly. So in this second case, the neural network is in some sense more sure that the answer is 0, right? And we should take that into account when creating the loss function, right? Why should we take that into account when creating the loss function? Because if you have a situation, say, I mean, something like this, where we have maybe 10, 9, and 2 versus, uh, you know, 25 and 2. And let's say that here the actual correct answer is in fact 1, right? It's not 2, it's not 0, it's in fact 1. Then this is a situation where the neural network is definitely performing better than this situation, right? And whatever a loss function is, it should be able to capture this minute difference in the output of the neural network. So it should not only look at what the current output is, or the output of the class that the correct class has. You should also look at the other classes, and it should not only look at the ordering, but it should also look at the relative values of these various scores. So all of these things should be taken into account when we develop the loss function, because otherwise, to the loss functions, if both of these situations are correct, we will really have no way of moving from one to another when we do an optimization, right? So our loss function should in fact be able to capture the difference in both of these two situations. To maybe even drive this point a bit more, we can have an example where instead of this 5, we actually have a 9 here, right? So everything is the same. It's only that the score of the 0 has changed, right? So if you go from row 1 to row 2, the loss function should tell us that, okay, no, something has gone wrong. Previously the network was almost sure it's a 0, now it's much more sure it's a 0. So it's definitely doing something worse in this case, right? So whatever loss function we come up with, it should be able to capture all of these kinds of things, right? So ultimately, what I'm trying to say with all of this is that we can't think of our network as simply producing a class when doing this optimization. We have to think of a network And this is again something that whoever answered mentioned. We have to think of a network as assigning a probability to each class, right? So you said, I didn't catch your name, but you said that the difference between these two cases is that the network is assigning more probability to 0 in one case, right? In fact, that is the key point that I want to kind of motivate by saying all of this, is that we can't think of a network as just producing a class, right? So in this particular instance, the type of our function, it can't simply be just some Rn, where Rn is the space of images to 1 of 0 to 9, right? This cannot be the type. The type instead needs to be Rn to a probability distribution over this class is 0, 1 to 9, right? 0 to 9. And this probability distribution again is going to, of course, be some value in R10, right? So it's going to be some value in R10, so the sum is 1 and so on and so forth, right? It's going to belong to some subspace of R10, not exactly the full of R10, but yeah. So, but the idea is that we want to finally produce a probability distribution over 0 to 9. We don't just want a class, right? So the neural network is already giving us some scores. How can we now turn them into probability distribution? Here is where basically this kind of a particular function comes in, which is what we call softmax. So this is what that softmax function is going to do. It's going to so the motivation for using this particular kind of function is that it does not care about the signs of your y0 to y9, because remember, a neural network it can produce an output of any sign. It's not even necessary that the scores need to be positive, right? So you can't just sum and then normalize, because then you can get negative probabilities which will not make any sense, right? So, but if you take an exponent of these kinds of y0 to y9 values, then what we would get is something that is definitely going to be positive. And then if we now normalize, so this is going to be sum over j of all of these things.
There should not be any one minus,
Yeah,
right?
there should be
Summation
one
of
minus. I think this is wrong. But anyway, this should just be Pij equal to e to the j e to the y cap ji divided by sum of e to the y cap ji. This is all that it should be, right? Yeah. So you now know that this guy is going to be greater than 0. And now if you normalize, what you would get is in fact something that can be safely interpreted as a probability distribution, right? So the reason that people call this a softmax is because in some sense, what we want to do is we want to take quote unquote the max of these guys, but we want to do it in a way that captures all the other relative values as well, which is what people mean when they say it's really a soft version of your max function. And if you look at this kind of probability distribution, this is what it will do. It'll if any one of your yi's is significantly bigger than everybody else, then ultimately what's going to happen is that that particular probability is going to be close to 1, everybody else is going to be very close to 0. But if one of your II is kind of close to another guy, then both of them will get assigned probabilities that are going to be similar, and so on and so forth, right? So this is the kind of behavior of this function, which is why people tend to use this. Okay, so now we have probabilities, right? And now our parameterized function approximator is doing something like this. It's taking an image and it's, and some parameters, and it's giving us a probability distribution, right? Now the second question is, how do we get a loss function, right? So we have a probability distribution over a bunch of classes, but we also know the correct class for this particular image. So what should a loss function now do given this information? So one way of answering this is asking really, what is the probability of seeing the current data that we have given this particular distribution, right? So given that we have some p to the j and so forth, right? What is the probability of seeing the particular data set that we have? So what is the data set that we have? For our data set just says that for image xj, the correct class is in fact cj, right? So what is the probability of seeing cj according to the distribution pji? It's simply pj cj, right? So now if you take this and take product over all of your images j, you finally get this expression, which is basically just the probability of seeing the data that you have, right? And the idea is that if your image classifier is doing something correct, the probability of seeing the data that you have should be high, right? So if we come up with an image classifier and it says that, oh, whatever data set that you have of these images is very unlikely to be generated, then this probability is going to be very low. And that just means that my classifier is probably doing something that doesn't agree with the data sets. In other words, it's likely that it's wrong, right? So we want this probability to at least be high. And we call this value the likelihood of this classifier, right? And this is a standard process whenever we have a parameterized distribution. This is a standard kind of measure of determining how well this particular distribution is doing. And the standard process of finding a correct value of parameterized distribution is to actually maximize this likelihood, right? Now, of course, we have this likelihood value, but what we want is finally a loss function. For numerical reasons and to make things a bit simpler, we usually take a log of this whole expression so that this huge product gets converted into a sum. And then we put a negative sign so that instead of having to maximize the probability, we have to minimize, the final expression that we get, we have to minimize it. And that basically gives us this expression, which is the negative of the log of these probabilities, right? Now, if you minimize this, you should end up maximizing the probability of you seeing your dataset, which means you should finally get a classifier that produces PJCJs that corresponds well with your dataset, which means you should, have a classifier that agrees with your data and works well, right? So this is the kind of motivation behind what is typically known as negative loss likelihood. So, okay. This is good, but there is one more, potential quirk that we want to cover. In some cases, what happens is in certain kinds of data sets, the data set itself is not just xj and cj, but the data set itself has, your images xj, and the data set itself might give you some probability distribution on xj, right? So it can give you that, okay, for this particular image, I don't know what the correct class is, but I can tell you that in the real world, so this kind of image appears with the class 0 with probability q0, right? Appears with the class 1 with probability q1, and so on and so forth, right? So this is something that can also happen in certain kinds of data sets. And you can imagine for an MNIST, for instance, if I give you an image that looks, something between a 1 and a 2, maybe some guy wrote something like this. Is this a 2 or a 1, right? It could, it could really be both. You can think of this as a 1 by saying, oh, this is really a 1 that looks like this. Or you could think of this being a very flat 2, right? So, it can kind of be both. And if I were to go to a human expert and ask it to assign it a class, then human expert might say, oh, I don't know, it's 50% 1, it's 50% 2, right? So there are some data sets where things like this can happen. And vice versa, what can happen is some image that is very, you can have in the same data set an image that is very close, two images that are very close according to pixel values, but one has a label 1, one has a label 2, and so forth, right? But in any case, in a data set, if your output is not just one class, but probabilities of classes, what do? You can actually extend this a bit. So you can think of it in this way, as in this particular data set, instead of thinking that you have 1xj with output probability distribution of q0 to q9j, you can say that, no, I'll draw many samples of this same image xj, and each sample I'm going to choose a particular class cj according to this particular probability distribution, right? So if you were to draw that many samples and then finally assign, assemble this particular loss function, then this term log pij, right, it's going to appear for as many samples where for this particular image xj, you drew the class ci, right? And that is going to happen with probability qji, right? Which means this term is going to appear, roughly speaking, qji times. So this should be a q, right? So then if we incorporate that into our expression, this is what kind of our expression becomes. And this, it turns out, can, is also can the same expression
So in
as
the so
called.
Digant, so the I and J have to be interchanged in the last bullet, is it? Written it Q superscript IJ, but in the actual slide it is I is
Oh
the
yeah. So it should be
J has to be down and I has to be
yes, J has to be
up.
down, I has to be up. Yeah.
No. But I guess no. I guess it's
No.
okay.
I think I have written it the other way around actually.
Yeah, you have written the other way around. I think what is there in the slide is correct. Yeah.
So this has to be, Q has to be, yeah. So, okay. So the I is talking about the particular data point and J is talking about the particular class that I have, right?
Mm.
So, yeah. So basically the probability of me producing class J for image I, for producing class I for image J,
Mm.
take the log and multiplying that with the probability of actually seeing class I for image J. And then you take the sum of that and take a negative. So that's the expression, right?
Yeah, it is. Then you finally minimize this over
Yeah,
a
over
lot of samples. Yeah. Hmm?
correct, exactly. And in fact, not just a lot of samples, you can minimize this over the whole data set. Like this summation J, here J belongs to the whole data set, right? And remember that these P's are actually the output of they're coming from some expression which is the output of your neural network. So these P's are really some much more complicated expression that have somewhere a theta within them. So ultimately, this whole thing becomes an expression of your theta. And when you minimize this, you would finally get a theta that works well for the particular data set, right? And the interesting thing is that this particular expression, this is also actually the same expression as that of cross entropy, which is another way, from for our perspectives, for our purposes, it's really another way of arriving at this same expression, but from an information theoretical perspective, which is you
Uh,
can yeah.
one logistics thing. I know we
Yep.
started late because you guys came in late, so I appreciate if people showed up early because if you yeah, normally if we start on time at 3:30, we can go till 4:45. People start showing up only at 3:40, which is what happened today. Then we might have to go a little bit later. Now I know some of you have class at 5 o'clock, or you have to catch shuttle at 5. So I'd appreciate if you guys show up on time. So then we can agree that we'll stop at 4:45. Today, since we started late, I'm suggesting that Diganta, you put 4:50. Okay.
Yeah, 450, I think I'll be done by that.
Yeah.
I mean, I have mostly
Yeah.
talked about most of the things
Yeah.
I want.
The point I'm making is if people show up late, then you will have to end up going late. Then your next class will be late, and so on and so forth. Yeah.
Yeah. So okay. So the reason that I went through both of these two slides was really to give you kind of flavor as to, if you were to set up a proper machine learning kind of experiment, what it looks like, and finally, what is this loss function actually going to look like for a very real world example? But do you have any questions about this? If you have any very detailed low level questions that we can answer, but also at a high level, do you have any questions about this and the motivation for any of these steps?
One comment that I had was for the to help the class. I know that we don't have any reference material, either in the form of a book or a paper or lecture notes or something like that. Now I know they have your slides and the lecture video. I know that this, so if they want, if you could provide some reference of some chapter where
Oh
it,
yeah, definitely. I think this is
that
actually
we should include it so that people can use that as a reference. Now, I think, yeah, the other comment that I wanted to add, so that Diganta, if you could do, then you can put it in the timetable. Yeah,
Yeah.
that thing. I guess if you could make a comment on how much they need to, well, it is good to know how this works and the gradient descent algorithm, because these are important to understand, gradient descent and back propagation and so on, because these are some of the values on which those algorithms will be operating, right? Will be working on. But for our own work, maybe there'll be some papers that will, when they are doing some verification of neural network, etc., these representations may become important, right? It's based to what the output it produces in what form and so on. But this is mostly used for the training part of the thing. Once the neural network or the machine learning model is trained, then how exactly the loss function, etc., is done is probably not that important for certain kinds of verification, unless your method is thing. Maybe I'm going, too far ahead. So I guess my question is, how much of maybe that is there on people's mind. How much of detail of this is about the exact structure and how this optimization problem is solved that they need to know for their later work in terms of verification and so on.
Yeah, so I think in terms of verification, that there's a lot of this can certainly be black box. But I think there is also an increasing number of things. For example, Alpha Beta Crown is going to use gradient descent to optimize.
Correct.
Again,
Yes.
yeah. So
So
there.
yeah, go ahead, please. Yeah.
No. So there. I mean, if one understands what gradient descent is at some concrete level, then mapping with that might be easier.
Yes.
But yeah, I think training of a neural network directly will not feed very directly into.
Correct. Yeah. So,
Yeah.
so I guess if I were to rephrase your questions, for people that are listening, generally it is good to know this, and especially if you want to understand, because there will be some verification techniques that use the gradient descent procedure as part of their verification, as part of that technique. Then you need to know a little bit of this, right? Depending upon
Yeah. Yeah.
certainly not the training part of it. Yeah. Okay.
Yeah.
That's the point that I just wanted to clarify and then reaffirm.
Correct. And yeah. So I mean, the motivation for me for these two slides was really to give a flavor of what it looks like to set up a loss function.
Yeah.
And then also the scale of the complexities of some of these loss functions that can be, and to reassure that a lot of these gradient descent based frameworks can handle these things well. So when something much more complicated shows up inside Alpha Beta Crown, for example, then it's not that difficult to imagine that will also work out. Okay, so I think I have some quick time, so I'll just quickly talk about how we actually optimize the cells. So far, what we have really only talked about is how to construct an L, right? Now, the question that I think we need to now answer is how do you actually optimize and find out theta given a particular L, right? So how do you optimize this L? And for this, we use this kind of a gradient descent algorithm and focus on the picture on the right hand side, right? So you can think of this L as producing a real value for any particular values of theta, right? So you have your theta 0 and theta 1. So let's say the theta in this case is a two-dimensional vector. So there's only two theta values inside your theta. And then L is going to produce some real value for each of these. So you're going to end up with a surface that looks like this. What you want to do is you want to find a low point in this surface, right? And one very kind of visual way of doing it is to start out somewhere random and just keep moving in a direction that is going to roll you down the surface. So again, come here, find a direction where the value of the surface is going down, move there. Find a direction where the value of the surface is going down, move there. and you keep repeating this. And if you keep repeating this, you will definitely keep going down, and you will get to a point which is at least going to be a local minimum, right? But there is, no guarantee that this process will get you to the global minimum. That is the first important caveat of using gradient descent, right? So for example, I could have started here and I could have ended up here. I could have started here and I would have ended up here, right? And there is a lot of various heuristics that goes into this kind of algorithm, but this is the crux of gradient descent, where you start at a point and you keep going down this loss surface until you hit at least a local minimum, right? So, you know, okay, so this will give you some value that will locally minimize L, and therefore a value of theta that is locally good. But what is the guarantee that there is going to be actually a good value of theta? Well, surprisingly, there is no guarantee, and it's really not very well understood why, but this seems to work amazingly well in practice. All of the great results that you see all across machine learning, all of them, all of the modern big results, they use neural networks to some capacity, and they optimize using this gradient descent, and they don't have any guarantee for going to the global minimum. They only have guarantees up to local minimum, and yet they're able to get all these results. So it seems to work really well in practice, which is very surprising. I mean, if you think of it from a point of view of what is the optimization guarantee here, right? So nobody really understands why. Maybe the loss functions are such that any loss, any value of theta that gives you a low value in the loss function turns out is also, very close to the globally best value of the loss function you can get. That could be one way. Or maybe these models are really not learning as well as we think we are, and the issue is that we're not measuring these models right. That could be another, potential explanation, right? And we'll explore kind of the second aspect, the second possibility quite a bit in this course when we look at robustness and things like those. But yeah, this is what gradient descent is, which leaves us only with one question, which I'll not go too much details into, uh, which is how do you find the derivative of L, right? Because, to find this direction in which the value of L will be reduced, the way that gradient descent does it is that it calculates the gradient of L with respect to theta, which means it really calculates the derivative of L with respect to each value of theta I, right? And the question is, how do you do that? Well, the way you do it is you simply, you take your L, and your L is going to just be ultimately a composition of various functions, right? So your L is going to be something like, um, you know, for example, if you take the previous example, the L is going to be something like, this, sorry, negative of log of some u, and then u is going to be minus e to the y by, so there's no minus over here, sorry. Yeah, e to the y by sum over e to the y, and then y is going to be, the neural network and so forth, right? So you can think of your L as being composed of these various kinds of functions, and what you can do is you can pre-compute, um, you have a library of what the derivative or the gradient of each of these functions looks like, and you can pre-compute that and redo this composition for all of those derivatives, right? So you know that, okay, given a particular value of theta, this, if L theta is simply minus log of u, that means that derivative of L theta with respect to u is going to be some function of theta, right? And then derivative of u with respect to y is going to be some function of y. So let's say that f1, f2, and then derivative of y with respect to your x is going to be some function of x, right? So you break down your L into these atomic components, pre-compute what these functions f1, f2, f3 should be at a level of library, right? Like you just have a long table of allowed atomic functions you can build your f out of, and corresponding f1, f2, f3s for those things. And then now you know that, okay, to compute finally del L del theta, or del L, let's say, so this guy should be a function of theta, let's say, del L del theta is going to just be del L del U times del U del Y times del Y del theta. And then each of these is going to come from each one of these of your functions. And you can just simply take this product and get your del L del theta, right? So there are very efficient libraries which achieve this. This is basically what most of your machine learning libraries are, which is just, this huge table of allowed atomic functions, correspondingly calculated derivative functions, and then a good interface to compose them, and a very good backend to compute these things very fast on specialized hardware like GPUs. So yeah, so this is how most of these machine learning algorithms calculate these derivatives. We don't really need to go into too much details of this. Just know that there is a very interesting set of machinery out there which we can maybe yeah, you can take a look at, and we can discuss at some point if people are interested. But yeah, this is all that I had to talk about. And are there any questions?
Okay, if there are no questions, I guess there are no. Okay, just give a peep, just for 30 seconds, what you plan to cover next time, so that just what do you plan to do?
Yeah. So next time I'll go into some of the more safety critical settings in which neural networks are applied, and I'll talk about robustness as a problem and why it's a very interesting problem. So we have been talking a lot about what these neural networks are, what they have learned, and what um, you, we expect them to perform. But there's a lot of underlying assumptions that I've kind of glossed over. So what I'll do is basically I'll bring those assumptions to the surface,
Okay.
and then say that if those assumptions don't hold, what would break, and show that that actually does break. And in reality, we don't really understand what these neural networks have learned, and that is a problem from a safety perspective. That leads to things like
No, but
brittle
how do you mean? You haven't talked about back propagation, correct? Yeah, so that is something that.
Yeah, so I don't. Yeah, I can cover back propagation in more details next time as well. So
Yeah, I think you should. I mean, I think you take two classes. One, I would want, I think in the list there is back propagation. Okay, so there you and also you spend. So
I can maybe talk about back propagation for something like 15 to 20 minutes,
okay.
Which means that I'll take maybe one class and then 15-20 minutes of something else.
Fine. Yeah.
Okay, sure. So I'll do back propagation, and then I'll do
Yeah.
robustness and safety of neural networks.
Okay, good. Thanks. When you upload the slides, it'll have all these markings, I presume, right?
Yeah, I always annotate the uploaded version itself. Yeah. So
if there are no more questions, then once again, okay, before, yeah, as I said, I know there are a couple of people, Pranika and Harsh, Pranika especially, he wants, I mean, if she's there, I mean, I see she's not there. Okay, the two things we'll have to decide before next class. And one is the time, okay, even if that means that for Thursday we'll have one time and then a regular time for the next 3 weeks. In either case, Shauriyam will interact, will ping you all to determine a suitable time for the online lectures. If some of you want to come in to CMI 2 and who want to physically sit there, if that's going to help to have a class, we can also discuss that, and then I can make provisions for you to sit there and listen to Diganta's lecture and the online lecture as in a class setting. These two things I will work with Shauriyam, the time, and if indeed some of you prefer to come in and sit in a class, physically in a class and listen, I will see if I can make arrangements for that, if that can help. Okay, so those two things I'll discuss and send confirmatory message on the thing. Yeah. Okay, on by email. Yeah. Moodle mail. Okay, thank you. See you.
okay.
Thursday.
Thanks everyone.
Thank you very much. Yeah.